Welcome to this walkthrough of LeetCode problem number 1094, carpooling. In this problem, we'll explore solutions to efficiently manage ride-sharing logistics while considering constraints like passenger counts and travel routes. Let's dive in and break it down step by step. The problem involves a vehicle that drives along a fixed route represented as a number line. The route includes specific stops, each denoted by an integer position. You are given a list of trips, where each trip specifies the number of passengers, the start location, and the end location. The goal is to determine if it's possible to pick up and drop off all passengers for all trips without exceeding the vehicle's maximum passenger capacity at any point. The input consists of the trips array, where each trip is represented as number_passengers, start_location, end_location, and an integer capacity that defines the maximum number of passengers the vehicle can carry. The output is a Boolean value, true if all trips can be completed within the capacity, and false otherwise. Here's an example to illustrate the problem. In the first example, we are given two trips. The first trip requires picking up 2 passengers at position 1 and dropping them off at position 5, and the second trip involves picking up 3 passengers at position 3 and dropping them off at position 7. The vehicle has a capacity of 4 passengers. At position 3, there are already 2 passengers from the first trip, and 3 additional passengers are picked up from the second trip, resulting in a total of 5 passengers on board. Since this exceeds the capacity of 4, the function returns false. In another example, the same trips are considered, but this time the vehicle has a capacity of 5 passengers. Under these conditions, the vehicle is able to handle all passengers at every stop. At no point does the total number of passengers exceed the capacity. Therefore, the function returns true. Now, let's look at a third example. Here, we have 3 trips. The first picks up 2 passengers at position 2 and drops them off at position 6, the second picks up 2 passengers at position 4 and drops them off at position 7, and the third picks up 4 passengers at position 1 and drops them off at position 8. In the third example, the vehicle has a capacity of 6 passengers. At position 1, 4 passengers are picked up from the third trip. At position 2, 2 more passengers are picked up from the first trip, bringing the total to 6 passengers, which matches the capacity but does not exceed it. As passengers are dropped off along the way, the total number on board remains within the limit. For example, at position 6, the 2 passengers from the first trip are dropped off, and by position 8, all remaining passengers are dropped off. Since the capacity is never exceeded, the function returns true. The constraints for this problem ensure that there can be up to 1,000 trips, with each trip specifying up to 100 passengers and stop positions ranging from 0 to 1,000. The capacity can be as high as 100,000. When solving this problem, it's important to consider edge cases. For instance, if there is only one trip, you need to check if the number of passengers exceeds the capacity. For overlapping trips, you must ensure that the total number of passengers at each stop is summed correctly and does not surpass the capacity. For non-overlapping trips, the solution should handle them seamlessly without any unnecessary computations. Finally, with large inputs, such as the maximum number of trips or a very large capacity, the solution must be efficient and scalable to handle these scenarios within the problem's constraints. When tackling this problem, one straightforward idea is the brute force approach. The intuition here is to simulate the entire journey by iterating through every stop on the route. For each trip, we increase the passenger count at the trip's starting location and decrease it at the ending location. Then, by iterating through the route, we calculate the number of passengers at every stop and confirm that the vehicle's capacity is never exceeded. While this method is conceptually simple and easy to implement, it's computationally expensive for large inputs. Specifically, the time complexity is O, n asterisk max_distance, where n is the number of trips, and max_distance is the length of the route. The space complexity is O, max_distance, as we need an array to simulate the route. To improve upon this, we can turn to a more efficient technique called the difference array. This method leverages the idea of range updates. Instead of iterating through all stops for each trip, we only adjust the values at the start and end points of each trip in an auxiliary array. This significantly cuts down on redundant computations. After processing all trips, we compute the prefix sum of the array to determine the passenger count at each stop and verify that no stop exceeds the vehicle's capacity. This optimization makes the approach scalable to larger inputs. This optimized technique brings a significant speedup by avoiding the need to simulate every stop for every trip. Instead of performing multiple iterations, the process becomes a linear scan, which is far more efficient. Specifically, the time complexity is reduced to O, n plus max underscore distance, where n is the number of trips, and max underscore distance is the maximum stop index in the trips. The space complexity remains O, max underscore distance, as the auxiliary array still needs to account for the entire range of stops. The strategy we've chosen for solving this problem is this difference array approach due to its combination of efficiency and simplicity. The key insight here is that we don't need to directly track the number of passengers at every stop throughout the journey. Instead, by focusing on the net change in passengers at the start and end points of each trip, we can quickly reconstruct the passenger count at each stop using a prefix sum. This eliminates unnecessary computations and ensures the solution can handle larger datasets effectively. Two important observations make this approach stand out. First, we only modify the start and end points of the trip, which drastically reduces operations, and second, the prefix sum allows us to verify capacity constraints in just one pass over the data. Now let's compare the two approaches and evaluate the trade-offs. The brute force method is easier to grasp conceptually and straightforward to code. However, its inefficiency makes it impractical for larger inputs, as it scales poorly with the number of stops and trips. On the other hand, the difference array approach is slightly more complex to implement but offers significant advantages in terms of efficiency. It avoids redundant computations and processes the input in linear time relative to the number of stops and trips. This makes it highly suitable for scenarios involving large datasets. Ultimately, the difference array approach stands out as the best choice for this problem. Its optimal balance of time complexity, which is O, n plus max underscore distance, and space efficiency makes it not only scalable but also practical for real-world applications where routes may involve a significant number of stops. By focusing on the net change in passengers and leveraging the prefix sum technique, we achieve a solution that is both efficient and robust, making it well-suited to handle the constraints of this problem. To solve the carpooling problem, we need to simulate the journey of passengers and verify if the number of passengers on board exceeds the vehicle's capacity at any point. The input consists of a list of trips, where each trip is defined by the number of passengers, the starting location, and the ending location. Additionally, we are provided with the vehicle's maximum capacity. Our goal is to ensure that the capacity is not breached during any part of the journey. This setup forms the foundation of our algorithm. The brute force approach begins by initializing the necessary data structures. Specifically, we create an array called passenger underscore changes to track the net change in passengers at each location along the route. The size of this array is determined by the maximum endpoint among all trips, ensuring it covers all possible locations. After setting up the array, we iterate through the list of trips. For each trip, we update the passenger underscore changes array by incrementing the value at the start location to account for passengers boarding, and decrementing the value at the end location to reflect passengers disembarking. This allows us to capture the cumulative changes in passenger count at every stop. Once the passenger changes are recorded, we simulate the journey to determine if the capacity is exceeded. We initialize a variable current underscore passengers to 0, which will keep track of the number of passengers on board at any given time. As we traverse the passenger underscore changes array, we update current underscore passengers by adding the value at each stop. If at any point this count exceeds the vehicle's capacity, we immediately return false, indicating that the trip is not feasible. If we complete the traversal without exceeding the capacity, we return true, confirming that the trip can be completed within the constraints. Let's illustrate the process with an example. Suppose the input trips are 2, 1, 5, 3, 3, 7, and the capacity is 4. First, we determine the maximum end location, which is 7, and initialize the passenger underscore changes array with zeros, making it of size 8. For the trip 2, 1, 5, passengers board at stop 1, so we increment passenger underscore changes 1 by 2. They disembark at stop 5, so we decrement passenger underscore changes 5 by 2. the array becomes 0, 2, 0, 0, 0, minus 2, 0, 0. Next, for the trip 3, 3, 7, passengers board at stop 3, so we increment passenger underscore changes 3 by 3. They disembark at stop 7, so we decrement passenger underscore changes 7 by 3. The final array is 0, 2, 0, 3, 0, minus 2, 0, minus 3, which now reflects the net change in passengers at each stop. Using the passenger underscore changes array, we simulate the journey. Starting with current underscore passengers at 0, we traverse the array. At stop 0, the count remains 0. At stop 1, it increases to 2. At stop 2, it stays at 2. At stop 3, it rises to 5, which exceeds the given capacity of 4. As a result, the trip is deemed infeasible, and the algorithm returns false. This example highlights the efficiency of the array-based approach, as it avoids repeatedly iterating through all trips at every stop by pre-computing the net changes. Additionally, it underscores the importance of handling edge cases, such as overlapping trips that surpass capacity, trips with identical start and end locations, and large inputs that require careful allocation of resources. The algorithm relies on two key data structures. First, an array is used to track the net passenger changes at each stop. Its size is determined by the maximum end underscore location across all trips, ensuring it covers all necessary indices efficiently. Second, an integer variable, current underscore passengers, is used to maintain the running total of passengers on board during the simulation. The time complexity of this approach is O, n plus m, where n is the number of trips and m is the maximum endpoint. This accounts for the time to record changes and traverse the array. The space complexity is O, m, driven by the size of the passenger underscore changes array. Together, these optimizations make the algorithm both time-efficient and space-conscious, suitable for handling large inputs. This implementation solves the carpooling problem by using a simulation approach with event sorting. First, we initialize an empty list called events to store all changes in passenger count at specific points along the route. For each trip in the input, we create two events, one for picking up passengers, positive count, and one for dropping them off, negative count. Both events are added to the events list. Next, we sort the events list by location to process events in the order they occur along the route. If two events occur at the same location, we prioritize drop-off events, negative counts, to ensure passengers are removed before new ones are added. This sorting step ensures the simulation is accurate. We then initialize a variable current underscore passengers to track the number of passengers in the vehicle at any given point. We iterate through the sorted events list, updating current underscore passengers for each event based on the change in passenger count. If at any point current underscore passengers exceeds the given capacity, we immediately return false, indicating that the trip is not feasible. If we complete the iteration without exceeding the capacity, we return true, indicating that the carpooling schedule is achievable within the given constraints. This approach ensures efficiency with a time complexity of O, n log n, due to the sorting step, where n is the total number of events, and a space complexity of O, n, for storing the events. In this implementation, we start by importing the necessary utilities and defining our solution class with the carpooling method. The method takes a 2D array trips, where each trip is represented by passengers, start, end, and an integer capacity representing the vehicle's capacity. The goal is to determine if it's possible to pick up and drop off passengers without exceeding the vehicle's capacity at any point. To achieve this, we use a list called events to store all pickup and drop-off points. For each trip, we create two events, one for the pickup at the start location, where we add the number of passengers, and another for the drop-off at the end location, where we subtract the same number of passengers. This ensures that we can keep track of passenger changes at specific locations. The events are then sorted based on their locations. If two events occur at the same location, we sort them by passenger change to ensure that drop-offs are processed before pickups, maintaining the correct sequence of operations. Finally, we initialize a variable current passengers to 0, which will help us track the number of passengers as we process each event. Now, we move on to processing the sorted events. For each event, we update the current passengers by adding the change in passengers at that location. If the updated current passengers ever exceeds the vehicle's capacity, we immediately return false, as it would be impossible to accommodate all passengers at that point. This condition ensures that the car's capacity is never exceeded during the journey. If we successfully process all events without exceeding the capacity, it means the carpooling plan is feasible. In this case, we return true to indicate that the trips can be completed as planned. This approach efficiently handles the problem by focusing only on the points where passenger counts change, ensuring optimal performance. To solve the problem, we start by examining the basic case. The input consists of 2 trips and a capacity of 4. First, we initialize an empty list called events to store all pickup and drop-off events. Next, we generate events for each trip. For the trip where 2 passengers travel from location 1 to location 5, we add a pickup event at location 1 with a value of 2 and a drop-off event at location 5 with a value of -2. Similarly, for the trip where 3 passengers travel from location 3 to location 7, we add a pickup event at location 3 with a value of 3 and a drop-off event at location 7 with a value of -3. At this stage, the events list contains all these raw events. Sorting the events by location gives us a structured sequence: first, the pickup at location 1, then the pickup at location 3, followed by the drop-off at location 5, and finally the drop-off at location 7. This sorted list will help us process the events in chronological order to track the number of passengers at any given time. With the events sorted, we now process them one by one to check if the capacity is ever exceeded. Starting at location 1, we handle the pickup event for 2 passengers, increasing the current count to 2. Since 2 is within the capacity of 4, we continue. At location 3, a pickup event adds 3 more passengers, bringing the total to 5. However, 5 exceeds the given capacity of 4, so we immediately return false. This means the trips cannot be accommodated with the current capacity. Moving on to the second example, the input now has 2 trips with a slightly higher capacity of 5. Once again, we initialize the events list to store pickup and drop-off details. For the first trip, where 2 passengers travel from location 1 to location 5, we add a pickup event at location 1 with a value of 2 and a drop-off event at location 5 with a value of -2. For the second trip, where 3 passengers travel from location 5 to location 7, we add a pickup event at location 5 with a value of 3 and a drop-off event at location 7 with a value of -3. This results in an events list containing all these raw events. Sorting the events ensures we process them in the correct order: the pickup at location 1, followed by events at location 5, and finally the drop-off at location 7. We then process these events to track the number of passengers. At location 1, the pickup for 2 passengers brings the total to 2, which is within the capacity of 5, so we proceed. At location 5, there are 2 events: first, a drop-off for 2 passengers, reducing the count to 0, and then a pickup for 3 passengers, increasing the count to 3. Since 3 is still within the capacity, we move to the final location. At location 7, the drop-off event for 3 passengers reduces the count to 0. At every step, the current passenger count remained within the capacity, so the output for this example is true. Now let's explore an example with multiple overlapping trips to see how the solution handles more complex scenarios. This input includes 3 trips and a capacity of 6. As before, we start by initializing the events list to store the pickup and drop-off details for each trip. For the first trip, where 2 passengers travel from location 1 to location 5, we add a pickup event at location 1 with a value of 2 and a drop-off event at location 5 with a value of -2. For the second trip, where 3 passengers travel from location 2 to location 7, we add a pickup event at location 2 with a value of 3 and a drop-off event at location 7 with a value of -3. Finally, for the third trip, where 1 passenger travels from location 4 to location 6, we add a pickup event at location 4 with a value of 1 and a drop-off event at location 6 with a value of -1. This gives us a complete list of events, which is then sorted by location. The sorted list ensures we process events in chronological order: pickups at locations 1, 2, and 4, followed by drop-offs at locations 5, 6, and 7. As we process the events, the passenger count evolves as follows: at location 1, the pickup for 2 passengers brings the total to 2, which is within the capacity of 6. At location 2, a pickup for 3 passengers increases the count to 5, which is still within the capacity. At location 4, another pickup for 1 passenger brings the count to exactly 6. At location 5, the drop-off for 2 passengers reduces the count to 4. At location 6, the drop-off for 1 passenger brings the count down to 3. Finally, at location 7, the drop-off for 3 passengers reduces the count to 0. Throughout this process, the current passenger count never exceeded the capacity of 6, so the output for this example is true. This demonstrates that the solution can effectively handle multiple overlapping trips by leveraging the event-based approach to track and validate passenger counts in chronological order. In this problem, the time complexity arises from 3 main steps. First, we create an events list by iterating through the given trips. Each trip contributes 2 events, one for the pickup and one for the drop-off, so this step takes n time. Next, we need to sort the events list, and since it contains 2n elements, the sorting operation takes 2n log 2n, which simplifies to n log n. Sorting is the most time-intensive part of the solution. Finally, we process the sorted events list to keep track of the current number of passengers and ensure that the capacity constraint is not violated. This step involves a single pass through the 2n elements, taking 2n, which reduces to n. Together, these steps define the time complexity of the algorithm. When combining these steps, the sorting operation dominates the overall time complexity, resulting in n log n. Next, let's consider the space complexity. The events list itself requires space proportional to its size, storing 2 events per trip, which adds up to n space. Additionally, the sorting algorithm typically needs temporary storage for its operations, which also requires n space in most implementations, such as timsort. Other variables used in the algorithm, like the counter for current passengers and any loop variables, take constant space, or 1. Therefore, the overall space complexity of the solution is n, driven by both the events list and the sorting algorithm's auxiliary storage. Now let's analyze the algorithm under different scenarios. In the best case, even if no trips overlap, we still need to sort the events list, so the time complexity remains n log n. Similarly, in the average case, the sorting step continues to dominate, keeping the complexity at n log n. Even in the worst-case scenario, where all trips overlap, the algorithm does not change. Sorting and processing the events list still dictate the time complexity as n log n. Comparing this to a brute force approach helps illustrate the efficiency of the optimized solution. A brute force method would simulate the entire timeline by iterating over all time units, checking how many passengers are present at each point. This approach would involve t*n time, where t is the total range of time units, which can be very large, making it highly inefficient. The brute force approach also suffers in terms of space complexity. It may require an array of size t to track the number of passengers across all time units, leading to t space usage. In contrast, the optimized solution avoids simulating the entire timeline by working only with the events list, which is both time and space efficient. Mathematically, the sorting step, with its n log n complexity, dominates the time analysis, while iterating through the sorted list adds only n. Together, the time complexity remains n log n. Space complexity is linear, n, due to the storage needed for the events list and the sorting algorithm's temporary space. This optimization is a significant improvement over the brute force approach, achieving both faster execution and reduced memory usage. When working on carpooling problems, there are a few common mistakes to watch out for. First, it's easy to forget to decrement the passenger count at the endpoint of a trip. This leads to an overestimation of passengers at certain stops, which may cause your solution to fail capacity checks. Another issue is neglecting edge cases, such as overlapping trips, trips that start and end at the same location, or scenarios where the capacity is matched exactly. These edge cases can expose flaws in your logic and result in incorrect outputs. Additionally, some implementations rely on a brute force approach, like iterating through every trip and stop, which can lead to n superscript 2, or worse performance. This is highly inefficient for large datasets and can result in time limit exceeded errors. Lastly, skipping the use of a prefix sum for optimization can lead to redundant computations, as a direct iteration over the route at each step recalculates data unnecessarily. Using a prefix sum allows you to consolidate these calculations, improving efficiency significantly. Another mistake to avoid is hard-coding values, such as assuming a fixed number of stops or constraints. This limits the flexibility of your solution and may cause it to fail for different input ranges. Shifting gears, let's discuss some tips for interviews. Recognizing patterns is key. Problems involving intervals, ranges, or capacity constraints often benefit from techniques like sweep lines or prefix sums. Identifying these patterns quickly can help you select the right approach. It's also important to focus on optimization. While a brute force solution is good for understanding the problem, you should aim to refine it into an O, n log n, or O, n solution. Always consider edge cases, such as overlapping intervals, trips without passengers, or scenarios where the capacity is matched exactly. Discussing these explicitly demonstrates a thorough approach. Finally, be ready to explain trade-offs. For example, you might highlight why a prefix sum is more efficient compared to directly iterating over the route at each step. This problem is closely related to several other interval-based challenges. For instance, LeetCode 253, Meeting Rooms 2, involves managing overlapping intervals to determine the minimum number of resources required. Of course, LeetCode 1094, Carpooling, is directly related, as it focuses on managing passenger counts at specific stops. Another similar problem is LeetCode 1229, Meeting Scheduler, which involves overlapping intervals when finding compatible meeting times. Lastly, there's LeetCode 56, Merge Intervals, where the goal is to combine overlapping intervals efficiently. Studying these problems can help you recognize and solve interval-based challenges more effectively, as they share similar patterns and techniques. When solving carpooling problems, it's also helpful to understand alternative approaches and their trade-offs. A brute force solution, for example, involves iterating through all trips and stops, resulting in a time complexity of O, n superscript 2, or worse. While it's useful for validating your logic on small inputs, it becomes impractical for larger datasets. A more efficient approach is prefix sum optimization, which has a complexity of O, n plus m, where n is the number of trips and m is the maximum stop index. Though slightly more complex to implement, it offers significant performance benefits for larger inputs. Another option is coordinate compression, which reduces the problem size by mapping stop indices to a smaller range. This approach has a complexity of O, n log n, due to sorting, and is useful when there are many stops but only a few are actually used. Finally, the sweep line algorithm is well suited for problems involving overlapping intervals or events. Its complexity is also O, n log n, as it requires sorting the events, but it's particularly effective for managing start and end points efficiently. Great job reaching the end of this problem explanation. We covered the brute force approach and discussed its applications and limitations. Remember to practice similar problems to strengthen your skills. Thanks for watching, and I'll see you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!